Good afternoon. I'm basically representing my co-authors today. And this is really an action title, right? But what I'll be talking to you about today is the work that we have been doing for the past year to accelerate velocity scenario generation. So what are the challenges we faced? How did we address them? Where are we today? And where do we plan to go next? So before I get going, a little disclaimer, please do not make any investment decisions based on what you hear in this presentation today. All right, so I'll start with velocity model building, which you guys are probably more aware of that than I am. But it basically is an iterative process. It involves alternating cycles of inversion and seismic migration with the goal of improving the seismic image. And more often than not, it will involve an intermediate step, which is velocity scenario generation. And for the purposes of this talk, I will be mostly talking about salt scenarios, though we are not restricting ourselves just to that. But I'll be using salt scenarios as an example of velocity scenarios. And this step really involves tweaking the velocity model in the expectation that it will result in an imaging uplift in a localized region of the survey. How does it look like? So if you look at the bottom three cartoons here, going from left to right, as you modify or perturb the shape of the salt in the shallow part of the survey, what you realize is the continuity or the structural continuity of the seismic underneath it starts to improve, which means velocity scenario generation actually has quite a significant impact on improving the seismic quality. So how does this look like in practice? What does it entail? Now, usually when salt scenarios are generated, how the velocity model is tweaked and how much it is tweaked is really driven by the target of the imaging uplift. And so a couple different domain experts might choose to tweak the velocity model in slightly different ways to, in fact, change the velocity or the seismic in the same region. So there's a fair bit of subjectivity involved in how the scenarios are generated. Also, there's a whole lot of variability that comes into the process that comes from the geographical location of the survey, the geological complexity, and most importantly, as we found, is how the prior knowledge and the domain expertise are informing the velocity scenario generation. That process tends to be highly variable. So given that this is subjective and variable, it tends to be a time and effort intensive process. So there's a whole lot of value in being able to accelerate such a workflow or such a piece of process. Not just in terms of how quickly you can generate a scenario, but it also gives you the capacity to build or generate multiple or many more scenarios than is feasible otherwise. And then that basically allows you to better exhaustively explore the uncertainty space, which is what scenario generation is meant to do. So once we started looking at accelerating velocity scenario generation, what we realized that the complexity of the problem would warrant a deep learning solution. So we took a stab at training deep learning models to accelerate this process. But what we realized is most of the model building projects tend to be time and resource constrained, and that manifests itself in terms of the data that is retained once a project is completed. So only the velocity scenarios that probably manifested an imaging uplift are retained, if at all. And the most important piece of data or that we end up missing in these at the end of these projects is that how the prior knowledge has been injected into the scenario generation. The data sources to inject that information are rarely consistent and rarely maintained after the project has been completed. So what that basically means is, if you want to train deep learning models, there isn't enough representative data available to really encompass all of the degrees of freedom that are required for emulating velocity scenario generation. So essentially, we hit the data scarcity wall. And at that point, we started looking out for other analogous solutions and how this problem is solved in other domains. And by analogous, I mean analogous in the sense of data scarcity driven by variability and the subjectivity of the domain. So one such application that we came across was lung segmentation from 3D CT scan images. Now usually physicians will do a very cursory lung segmentation by looking at the CT scan images. And then, as you can imagine, tends to be highly subjective. Another physician might make a very different call as to the shape of the lung. The variability actually comes into this application because of the wide range of pathologies that exist from different patients. And the pathologies significantly affect the shape of the lung. So very similar in terms of subjectivity and variability, and hence the lack of training data that can be used for deep learning model. However, this process is significantly accelerated today through computer-aided diagnostic tools. But how do they do it? So that's kind of what we started to look at. And what we realized is behind the scenes, they are really using traditional computer vision algorithms to be able to accelerate this process. So what is done today in most of these tools is you will probably start with a very initial generic segmentation of the lung. And then you will bring specific patient information into the picture in terms of the rib cage information of that person. So what that allows you to do is now give you sort of a spatial context within which your lung should exist. And then you go further and you are going to bring in pathology-specific information driven by the data. And now you will basically refine your segmentation within this spatial context and within this data context. So can we do something very similar, use very similar building blocks for accelerating scenario generation? So we thought we would take sort of a different look at how we can approach scenario generation. And so again, I'll be using solved scenarios to explain this, but given an initial shape of the solid, can we figure out the size and the places of the solid that we really want to perturb? Are there any pieces of data that are typically available within the velocity building project, model building project, to be able to leverage to do this? And the second step becomes, if we figure out what are the perturbation areas or how we want to change the shape of the solid, can we then go in and put in various different velocities to generate multiple scenarios? So what we ended up doing is we are currently leveraging the velocity deltas that are generated from a typical inversion cycle, and we are using these deltas to really inform or figure out which areas of the salt should be perturbed. And then we allow the user to inject their domain experience and their domain knowledge into the process by giving them a whole range of velocity variations that they can inject into perturbation areas. So what we have built currently is we have built a tool which has two sets of building blocks. One is a set of data-driven building blocks, and another is a set of spatial building blocks which allow you to inject the data and the spatial context in the perturbation space. So what we have currently is we start with a velocity delta map coming out of a typical inversion cycle, and we use different types of spatial constraints or spatial guidance, if you will. One of the spatial constraints could be the initial salt mask, and using those two pieces of information, we take the velocity delta map and we only select those pieces of velocity deltas that are able to perturb the model where we want it to be perturbed, right? And once we do that, we go in and change the velocities within those perturbation areas to now generate multiple scenarios. So what do we have today? We have an adaptive and accelerated tool for velocity scenario generation that we have built, and it is able to generate scenarios in an accelerated manner, similar to what you see in the animation on the slide here. So how did we do this? We basically built functional building blocks from traditional computer vision workflows, And what we allow the user to do is take these building blocks and customize their workflow for the specific needs of their project, so that they are able to account for all of the variability and the subjectivity in a particular project. So fine, we are generating these scenarios, but what we wanted to also make sure was, are these scenarios realistic enough to actually generate an imaging uplift? So what we did was we took these scenarios and then we migrated them and tried to look at the targeted region where we were looking for a seismic quality uplift. So what if you see the panel that is on the left side is really the panel coming from the baseline velocity model or the initial velocity model. The panel in the middle is seismic from one of the scenarios that we generated, and the panel on the right is another scenario that was migrated. So if you look at the panel in the middle and specifically sort of look at this area, right, this salt sediment boundary, and you compare it to the initial migration, what you see is we are able to better highlight the contrast between the salt sediment boundary. So we did indeed realize the seismic uplift through one of these scenarios. However, if you look at the panel on the right, what you will see along the very same boundary is that there was a bit of a degradation in the quality, which is the nature of velocity scenarios, right? Some will give an uplift, others won't. So basically, this was a proxy QC for us to say, hey, we are on the right track. We are generating realistic scenarios. So with this slide, one of the things that I wanted to highlight is not just that our workflow is adaptive and accelerated, but it actually is quite versatile. So we are not only limited to generating salt scenarios. So if you look at the panel on the left, this shows an example of a deep sediment update or a deep sediment scenario. What I wanted to also highlight here is if, I think I went to the next slide. Sorry. Highlight here is also, this is sort of the velocity delta map that is coming out of the inversion. And what you can see highlighted here is we have managed to isolate just these areas from the velocity map to actually determine where and how we want to perturb the sediments. The very similar thing you can see on the panel on the right, except we are realizing a shallow sediment update here. Moving on to the next slide, very similar examples of the variability in terms of the versatility of the tool. The panel on the left is highlighting an intra-salt scenario, whereas a panel on the right, it really is a really good example of being able to realize a salt root extension kind of scenario, which ends up adding a piece of salt to an existing salt body. So that brings me to my final slide, which is kind of a summary, but also to give an idea of what our current challenges are and where we plan to go next. So if you look at what we have today, we have a tool that we have built and we have been actively deploying in many velocity model building projects. And while doing so, we are actively mining this data. So the data that has gone into velocity scenario generation, the scenarios that were generated, which resulted in an uplift of the seismic versus even retaining scenarios that didn't do that. The other thing that we do systematically is also track the pieces or sources of data that were used to inject specific domain knowledge and specific prior knowledge to inform scenario generation. So we are mining all of these pieces of data as we move along. But one of the challenges that we're currently also facing is that this workflow or this tool is heavily user driven. So we do depend on the user to be able to inject the prior knowledge into it. So there's a fair bit of parameterization that the user has to do. So the question for us becomes, how do we go from something that is simply accelerated to something that is more automated? And that's where all of the data that we have been mining comes into picture, because it is now enabling us to start training deep learning models to automate particular pieces of this workflow. So the idea is now to go not just to acceleration, but to automation of velocity scenarios. And the hope that we have is this will help us take the first steps towards bringing intelligence to the process as well. All right, that's all I have for you. Thank you for your attention.
Thank you very much. Any questions for Apurva? Oh, got one over here.
Hi, I wonder if you could clarify where the scenarios are coming from. I thought I heard you say they were coming from maybe the full waveform inversion deltas or misfits. And I guess in a full waveform inversion, those are injected back into your model to get the updated velocity. But how do you generate more than one of these scenarios from a full waveform inversion iteration?
So it really depends on the area of the where we are trying to realize the seismic uplift, for instance. So if you look at, let me try to go back. Yeah, in the panel on the on your right, I suppose that's where we took the deltas coming from full waveform inversion, and then we managed to isolate that area. But that is just one scenario essentially, right? And then you go in, manipulate the velocity within that area in many different ways. So that gives you, let's say, 10 scenarios. But what we can also do is we can manipulate the shape of the delta as well. So we can grow it, we can shrink it, and we can actually either attach it to the salt body or detach it from the salt body, and then subsequently we also change the velocities. So that's where the multitude of variations come from, even if the original perturbation is driven by a single velocity delta. Does that make sense?
Can I have a comment on this? Oh, I'm sorry. Usually when you have what we call a multi-client, you don't have many scenarios, but when you have a proprietary which is smaller or better, you can run tests like these because these are also takes time and take interpretation, whether FWI or whether the other scenarios. So basically it depends on the mass of the projects and if you have many owners or something. Okay? So that's what I wanted to add. Thank you.
Question over here. So you mentioned data mining on that. Are you using past projects that you guys have online and following along and saying how the geophysicists and the interpreters have modeled these plausible scenarios as data sets to mine and are labeled or anything like that?
No, so right now basically this is a tool we have built, right? And we apply this tool in live model building projects as the tool has been developed, and we're mining the data from those live projects. So we're not really using a whole lot of legacy data, at least to train the deep learning models. It's really generated from the projects that are running today.
And it's following along with what the interpreters are doing, and so it's learning from what they're doing on this one.
That's right. So we do mine the data sources for that the interpreters or the processors are using to realize the scenarios. So I showed you an example of the salt mask, for instance. That's one way to constrain the scenarios. But we allow them to bring in their sources of other sources of data, like horizons, for instance, to generate them as well.
And the reason you're not doing the legacies is just too it's too unknown on there.
Not just that, it's not always that these pieces of information are retained from legacy projects. That's really where the data scarcity issue really originates from. So that's why we pivoted towards traditional computer vision, and now we are at a point where we can generate lots of data, lots of representative data to train our models. And so now we can take on the deep learning aspect of this.
Okay, thank you again very much.
Thank you.